First few questions are just kind of reviewing. Hey, what do you remember what we just did here? We have a cart that is slowing down while moving away from the origin. So we're moving to the right and we're slowing down. And we have 4 different position and velocity graphs here, and you want to figure out which one corresponds to the motion. What I would recommend here, generally speaking, it is easier to look at the velocity graphs to try to match things up. And if you can base things purely on the velocity graph, fantastic. If not, then you do have to end up looking at the position graphs. But velocity graphs tend to be easier to understand and get information out of. And the last thing I'll say about this problem, sometimes it is easier to rule things out before you decide what actually is correct. It's kind of a better way to go about it. But anyway, throw a letter in the chat when you think you know what graphs work here. A lot of people saying D. All right, well, now, before I talk about if D is right or not, are there options that I can just straight up eliminate right now? Just get rid of? You bet. Our velocity is positive, right? We're moving to the right, and it's positive. Anything that shows a negative velocity is automatically incorrect. So that means C is out, and B is out. We are not moving to the left. C and B gone. Now we got A and D to work with. What's the difference between these two? Well, A shows speeding up, right? We start at a 0 speed, and it gets larger and larger. D starts off with a speed, positive, but then starts to go down. So it looks like D is our answer. D is our answer. D is definitely the answer. All right, and we base that pretty much just on the velocity graphs. I did not really need to look at the position graphs. Let's just look at this position graph, though, and make sure it makes sense. It says we start at the origin, which it does say in the problem we do start at the origin. And what this graph is showing is that we initially are traveling a bit in distance, but then as the time goes on, the rate at which we travel the x distance starts to go down. And that's slowing down. So these two graphs are consistent with each other, and they do explain what the motion is perfectly fine. Fantastic. So now, let me get rid of my things here. We have a very similar problem. Now we're moving to the left, and we're speeding up. So again, try to pick the correct position and velocity graphs. All right. Got a few people coming in with B. Well, let's just see about that. Again, I'm going to do the same thing I did last time. Can I eliminate answers right off the bat here? Our velocity is negative, right? Anything showing a positive velocity needs to get the heck out. So let's get this. What about A? I don't think so. A, get out of here. You're wrong. It's not a positive velocity. B, you got the same problem. D, you're a little different, but not different enough. You're out. It's answer C. I eliminate A, B, and D straight away. Well, let's just see. Let's make sure C makes sense. What does C say? Start at rest, apparently, and we speed up moving to the left. Well, yeah, basically. I mean, I didn't say we start at rest, but, it's still consistent with the motion. What's this position graph doing here? Start off in a positive position, we head towards the origin. You bet we're doing that. C's right. C's it. We got it. C's it. Like I said, maybe sometimes better to eliminate the wrong options, because sometimes it's easier to see something being wrong than being right. And if you're lucky, you eliminate all the wrong options, and then you're left with what the right option is. But then you should definitely spend some time looking at that and saying, well, why is it right? Make sure you understand why it's right. Okay. Now, we've exhausted our position and velocity graphs. We've done pretty much as we can with them, almost, I would say, actually. The last part of all of this is to incorporate accelerations into all this stuff here. The definition of acceleration is the rate of change of speed over time. So that would be a delta V over a delta T, which is a slope. Right? That means accelerations can be gathered from looking at the slopes of velocity versus time graphs. Now, the velocity versus time graphs would need to be, straight lines. Any curvature would not be a constant acceleration. And we don't do, in these first few chapters, any problems where the acceleration is continually changing. I mean, we may have a situation where the acceleration just dramatically switches at one point, and you see some examples of that. But either our accelerations are either zero or constant. Okay, we have enough to worry about there, without having to worry about changing accelerations. But units, just to be clear, meters per second squared. It's a vector, but we saw that, previously in what we did. Let's just jump right into a problem, though. Here is a velocity versus time graph for a basketball player moving up and down the court. And we would like to figure out what the acceleration versus time graph is. It says draw a motion diagram. This example, I'm just interested in getting the acceleration versus time graph. Now, before we do that, you want to look at this graph and try to understand what's going on with the motion. And I recommend you always do that with graphs. When you're given graphs, before you do anything else, look at it, try to understand what is happening. Okay, so let's do that with this one. At t equals 0, our basketball player is running to the right, and they are accelerating. In the first 6 seconds, they go from 0 to 6 meters per second. Okay, so there is an acceleration. It's positive, and if you work out the slope of this line, you will get 1 meter per second squared. Right, 6 seconds, 6 meters per second, done. After 6 seconds, our velocity is still positive. We are still moving to the right. However, we have this corner here indicating some kind of dramatic change in the acceleration, and we're no longer speeding up, we're slowing down at a much faster rate than before, because we go from 0 to 6, or 6 to 0, I should say, in now 3 seconds. It's really up the pace here. And if you work out this slope, you get a negative 2 meters per second squared. So for the first 3 seconds, we start to slow down. At 9 seconds, we have turned around. We went from positive to negative velocities. This is the turning point. And then we start to head in the other direction for the next 3 seconds, and we end up at a negative 6 at the end of it all. So that's what's going on with the motion. If I had to talk it out, I just did. There it is. So let's look at how the acceleration graphs would look like. We worked out these accelerations. They were the slopes of these lines, and that's worked out up here, so you can see the math there. But to draw it, we're going to draw this in 2 different parts, because there are 2 different accelerations. For the first 6 seconds, we have 1 meter per second, so I draw a straight, flat line. And then our acceleration sort of dramatically jumps, okay? Which, we don't know the details of that jump, and it's probably not even important for the problem. So when we have these kind of jumps here, I draw them like step functions, and I have a little dashed line indicating we had some kind of instantaneous change in a quantity. And then we come down here to negative 2 meters per second, which we maintain up until 12 seconds. And that's the acceleration graph. The acceleration graphs are a lot easier than the other graphs because there's only 2 scenarios you have. You either have 0 for acceleration or some constant value. That's it. So that makes that a lot easier. Right. Now, we have the same questions from the beginning, but now we are interested in velocity and acceleration graphs. So in this example, our cart moves to the right, and we're slowing down. So what will the velocity acceleration graphs look like? All right, A's and C's, huh? We don't know which one, A or C. You don't seem to like B or D. Why? Let's see here. Our velocity is positive. So D is very wrong, right? D is wrong. D is wrong. You've been condemned. Out. All right, what about the other ones here? A, now the velocity is positive in A, but it's showing speeding up. So, sorry, A. You're out. No way. C and B, they're showing a positive velocity that slows down. Great. Now let's look at the acceleration. Now remember what it means to slow down. We talked about this a couple lectures ago. Slowing down is when your velocity and your acceleration vectors point in the opposite direction. So if we have a positive velocity here, we're going to need a negative acceleration. That is indicated in C. So B is wrong. The answer is C. The answer is C. All right. Anything unclear about that example? However, I'm always trying to work with the velocity graphs. And if I need to go to the acceleration or any other graphs, I do. But velocities tend to be a little easier to work with, a little more meaningful. So, all right then. So again, same question as before. Cart speeds up to the left. What's the right acceleration velocity graphs? Let me know. Few C's, got a D in there. All right, let's go through it. I'm going to do the same stuff I always do. My velocity is negative because this points to the left. Can I rule things out? You bet I can. I'm going to use these nasty red X's. I wish they were larger, but they're not. Is there any positive velocities in here? Yes, A. You're done. Don't want A. Don't want B. No good. C or D is fine. And the difference between these two is one acceleration is positive, one's negative. We're speeding up. So if the velocity is negative, so must the acceleration. And therefore the answer is C. There we go. C. In fact, not only is C right, but the other ones are physically impossible, actually. You can't even do some of this stuff. In fact, I'm pretty sure you can't do any of it. Let's look at D. D shows an object that moves to the left and speeds up. But it has a positive acceleration. That's impossible. You can't move to the left with a positive acceleration and somehow speed up. You should be slowing down. So that doesn't work, period. That's nonsensical. What about B? Slowing down, moving to the right, but our acceleration's to the right. We should be speeding up, not slowing down. B doesn't make any sense. B doesn't work at all. And then A is the same deal. So A, B, and D just are impossible to do. You can't even do that stuff. So not only is C right, the other ones are just very wrong. All right, not any physics that I know about, at least. Okay. This question here is hard. I'll just preface this by saying it's pretty darn hard. We have an acceleration graph that shows a zero acceleration for a while, then instantaneously a negative acceleration for a time, and then back to zero. So which acceleration versus time graph or graphs would work here? Notice I'd say graphs. Maybe more than one works. A lot of A's and B's rolling in here, and I'm pleased by that. So this is a harder question for sure, and the answer is A and B both could be right. They both could be right. We don't have enough information to distinguish between A and B, though. So what are we told? The particles initially move into the right. Okay, so we have to have an initial velocity that's positive. So C is wrong. Now, if we're moving to the right, we have a negative acceleration that we're going to experience. That should slow us down. Now, A and B are showing that we're slowing down. The question becomes this. Do we slow down enough to actually change direction? Because this acceleration is going to change our speed. Are we going fast to begin with? Merry Christmas. Yeah, Ring or Alexa, whoever. I don't know. I got a bunch of robots in here that control everything I do. All right. I'll figure out one day. a fair one day. That I mean, I think I told you, like, I can't figure out how to get that off of there. I've had this for a year. It was like July and still Christmas carols, whatever. All right. Anyway, what I was saying here is that we have some initial information. We're moving to the right. Okay, but how fast are we moving to the right? Is it turn us around or not? And we don't know. We can't tell. So they're both potentially correct. D is just like, I don't know what the heck's going on with D. D is just being a weirdo. Doesn't make any sense. So okay. Yeah, you can't have an acceleration and your speed's just 0. Doesn't work. Okay. Let's do an example now. We have a velocity graph and we want to determine what the acceleration is going to be. So we're going from velocity to acceleration. That means we're looking for slopes. All right? So let's do it. Here we go, right here. So from 0 to 8 seconds, we are, well, let's see what's happening. We start off moving to the left, but we're slowing down. At 4 seconds, we turn around and we start to head to the right. For another 4 seconds, when we get to 8 seconds, we turn the acceleration off and we just kind of coast for the next 2 seconds at 2 meters per second. So that's what the motion's doing. That's what the motion's doing. So what is the slope here? Okay, well, I happen to just choose the area between 6 and 8, but it doesn't matter because it's all the same. But the slope of this line is positive 0.5 meters per second squared. So that's it. So I'm going to draw a flat, a horizontal line for acceleration at 0.5 for 0 to 8 seconds. I draw a little dash line because after 8 seconds, we are not accelerating anymore. So I just draw a line that's 0. And that is the acceleration graph, right? Pretty simple. We're going from velocity acceleration. We're thinking about, our slopes here. All right, any questions about that? Is that clear? Okay, so let's see here. All right, we're going to take a break right now, okay? We're 40 or so minutes in, but this is a natural spot for us to take a break because, well, I'll tell you after the break. How about that? So we're going to take I don't know. How about come back at 11:50. That's about 8 or 9 minutes. So I'm going to come back at 11:50, and then we'll continue on with the rest of this. Yes. We are transitioning here. We're segueing from graphs into more equations. So we've spent a lot of time developing position, velocity, and acceleration time graphs. And we've done that for a couple of reasons. One of the reasons is it helps us to understand and describe the motion that we see in a somewhat more analytical way. And so there's a lot of benefits to that. And we see the relationship between all these quantities through calculus, which is kind of neat. The second reason we do this is because the graphs allow us to develop equations that can help us solve our problems. And we have an equation already, and you saw it. It was the constant motion equation that's just basically rate times time equals distance. From your velocity graphs, like this velocity graph here, right? If there is acceleration, well, this is just a straight line, linear, right? And so there's another equation that we can come up with here, which is simply, what this equation really is? It's just the definition of acceleration, just rewritten, right? So final velocity equals initial velocity plus acceleration times delta t. That just really comes from the definition. So actually, both of our equations so far are just really based on our definitions. This Fs and Is, just to be clear what that means, this means final velocity in the s direction, whatever s is, could be x, y, whatever. It's just generic direction. And this is initial velocity in the s direction. Okay, so that's another equation we have. Well, this equation here, this velocity equation, involved acceleration. So that means we should be able to go back to the first equation that we worked out and try to see if there is any kind of alteration that's going to need to be made to apply acceleration. So if you look at the first part of the equation, that's familiar. That's what we developed before. And then now there is a second part to it. Second part is a 1/2 a delta t squared. And that's an additional term that's added if there's acceleration. So where does this come from though, right? So let's look at this. Look at this graph in the bottom here, right? The graph in the bottom here shows an initial velocity at initial time. Now, if there wasn't any acceleration, right, you would just have a straight horizontal line that goes across, and that would create this rectangle on the bottom. But that rectangle is right here. It's the v times delta t, so that's already there. It's the region above it that's of interest to us. The region above that is a displacement that has been gained due to the velocity increasing. And you can see what that is here for a straight line that creates this triangle. Right? The triangle has a base of delta t and a height that would be the difference in the two velocities. But from the last equation, that's equal to a delta t. And so we can just simply calculate the area of a triangle, which is 1/2 times delta t times a delta t. So put that all together, you get 1/2 a delta t squared. And this represents an additional amount of displacement or position, you can say, as a result of acceleration. And so that's an additional part to this equation. Okay. Now, there is a third equation that you can get, but you don't get them from the graphs. The two equations we have so far, one is based on position and one is based on velocity. They both involve units of time. Okay? Both involve units of time. But there's a lot of times there's situations where we don't want to have time, or we don't have time, or we don't want to worry about time. So what you can do with those is you could take those two equations, this is what you see right here. The top equation is the velocity equation, and the second one is the position equation. One of the things you can do is you can take that top equation and solve for delta t, and then plug it into the second equation, and then clean that up. Now that's not a fun exercise, I'll just tell you. Plugging this stuff in and doing all the algebra is a little bit of a nightmare, but if you persevere through all that algebraic gauntlet, I'll put it that way, you'll get the equation at the bottom, which is independent of time. And these are what is known as the kinematic equations for constant accelerated motion. Okay. Now, I like to label these things in this manner. The first one is what I call the velocity equation, or I call it equation 1. The second equation is the position equation, or displacement equation. You can say either way, because you can move the the S over here to create a delta. But I call this equation 2, or the position displacement equation. The last equation I call equation 3, and I call that the velocity squared equation. So sometimes I'll mention them by numbers, sometimes I mention them by what they contain. But these three equations are all you need to fully explain and describe motion of an object. Now, this applies for constant acceleration. Obviously, if you have no acceleration, all the a's become zeros, and you can see that everything simplifies to a great extent. And these three equations can be applied for any constant acceleration. Now, if the acceleration were to change at any point in the problem, you could still use these equations, but you have to create like a different set of them that apply to the other part of the motion, and I'll explain that later. It's like the basketball thing, how we were going one direction, and then the acceleration changed, and we were going the other direction at some point. We'd have to have two sets of these equations for the two different types of accelerations that exist. Okay, but now we're ready to really start throwing numbers behind things. right? And that's what we're going to be doing for the remainder of this lesson here. And then we're getting into a little bit of gravity at the end of this. All right, so let's recap the graph stuff before we really leave it. Now, we're not leaving graphs entirely. Just make sure that's clear. We just exhausted everything we can do with our graphs, but you'll see graphs again. Don't worry about that. But what you see here is basically the only two scenarios we can have in kinematics: either constant velocity, which is a straight line for position, horizontal line for velocity, and a zero acceleration. The other scenario is a constant acceleration, which excuse me, which would have the position as a parabola, and the velocity is a straight line, and the acceleration is a flat horizontal line. Okay. And as you sort of saw as we went through this, all of these things are related by calculus. Right? Now, again, I realize that not everybody's had derivatives yet. I mean, I don't know. Who's in 150 right now? What are you doing right now? Are you on limits? Are you past limits? Like, what's going on with you 150 people? Anybody new? I think everybody fell asleep.
I think the last thing we've been studying is derivatives. Like, we just got on it.
You really? Did you learn power rule for derivatives by chance?
I think we just barely got to that.
Okay. Well, we don't need to have an exhaustive understanding of calculus here. It really comes down to just, two things. Graphically, what does it mean to have a derivative, right? Slopes, right? That's what's going on here. When you go from position to velocity to acceleration, you're dealing with derivatives, and therefore you're dealing with slopes. You're looking for slopes. When it comes to integrals, you're looking for areas. And you can go from acceleration to velocity to position with integrals, and that's working out areas bounded by the curves. That's as much calculus as you really need to know, besides maybe a simple power rule. And I'll do a power rule problem before we're finished today. But nothing too heavy, I will say. Nothing too heavy. Well, if you're past 150, you're in a great spot. A great spot. I don't think anybody past 150 is necessarily at an advantage, but who knows? I don't know. Excuse me. All right, now, in order to use our equations to solve our problems, sometimes these problems are pretty simple and straightforward, and they're very easy to punch out, and sometimes they're actually a lot more complicated. And so what I like to do is I have a sort of system for solving problems. And I'm going to introduce what that system is and show you some examples of it. The system I developed is developed with consistency in mind. No matter how hard or difficult a problem is, this method can be applied to solve the problem. In a lot of cases, it's like overkill. It's a little too much, for what the problem asks for, but, that's okay if you're sort of learning the system here. But I think it's very important to have like one method that just works for everything. And that's true, this does work for everything. But it's something you definitely have to practice, and see a lot of examples of, and you sort of, with experience, figure these things out. Do you have to do this for every problem? No. Am I going to require you to do things this way? No. However, I do strongly recommend you do things this way because, for one, I think it works and it's a great method. And two, it just helps with communication. If you're doing the problems like I'm doing the problems and you're doing the problems like the other students are doing the problems, then it's a little easier to communicate. So, but like I said, if the problem's easy, you don't have to do a lot of these things. But if you find the problem very difficult, you might want to take a step back and go through this stuff and sort of see if that helps. So what is this method? Well, when you read over a problem, I think one thing that's very important is to draw a picture. And these first three steps are all about visualizing what you're seeing. I know for me, when I took physics, I really needed to see what was going on. If there was not a figure attached to a problem, I made sure I draw out as best I could what was going on, because once I start to see things, you start to pick up stuff that is difficult to just pick up when you're just reading a bunch of words. So you might find it helpful to draw a motion diagram of the motion. You definitely need to establish some kind of coordinate system, and that can be part of the motion diagram, where you decide, okay, where's the origin? Which direction is positive? Which direction is negative? And then any kind of sketch of the situation, that's not necessarily as important. It's just like sketching things out. Usually just the motion diagram and the coordinate system is sufficient. But sometimes you can just skip this stuff if you just want to see a picture of what's going on here. But this is really helpful for understanding what's being asked and how to go about solving it. Once you have everything drawn out, then you want to start to define things, define symbols. What's the initial positions for things? What are the final position for things? Is there anything interesting happening in between that I need to mention here? In the process of doing that, you want to make sure very clearly what things you know and what things you don't know. For the things you don't know, are they things that you need to know eventually to get to your answer? There's a lot of situations where there's information we don't know and we don't need to know it, and it's not important for the problem. So it's good to try to identify what things you need to get to the solution. This is all very broad and a little vague, I agree. That's why you're going to see some examples. So let's just jump right into an example right now, and I'll show you how I utilize a system like this to solve a problem. So here's the problem. We have a car that accelerates at 2 meters per second squared along a straight road. It passes two markers that are 50 meters apart at times 4 and 5 seconds. What is the car's velocity at t equals 0 seconds? Now, I'm doing this problem for a specific reason. Personally, I think this problem is challenging if you don't know this system. Okay, can it be solved? Of course it can be solved. You can solve this problem, but I like this example because it's sort of challenging, and the system that I've developed here will allow you to solve this problem very easily. But without that, it's a little bit difficult to figure out what's going on here. It's an awkward problem, really. The information they give you is a little strange. So let's look at it. I'm going to jump to my notes here. Okay, so let me go through this very carefully. I decided to start with a motion diagram. Sorry, let me get everything centered here. Okay, here we go. I decided to draw a motion diagram of what the car is doing. I've chosen 6 points because I want to kind of have each point represent seconds. All right, so I got t equals 0 seconds here, 1, 2, 3, 4, 5 seconds. Right. And I'm showing my car gradually speeding up, so the vectors are getting longer and longer and longer. My accelerations are in the same direction. I've labeled these vectors 1, 2, 3, 4, 5. Okay. So that's the depiction of the motion. I don't need to draw a car because I can't draw cars very well. I'm not even going to try to embarrass myself by drawing a car, but that's sufficient for seeing what's happening here. Now we want to talk about variables and what we know and what we don't know. And here's what I do. At the start of motion, you want to specify what the time, position, velocity, and acceleration is. At the end of the motion, you also want to specify time, position, velocity, and acceleration. Okay. Now, there's an intermediate place here, right? Now, normally you always put your information at the start and at the beginning, and in between, every time something significant happens, like you're given information about something, or somehow the motion changes and you want to incorporate that. So I'm including things at 4 seconds here. So I have decided for time and position here, now those are part of the coordinate system. So I can specify these things to be whatever I want them to be. So I'm just going to say t equals 0, x equals 0, right, for the start here. I don't know what my initial velocity is, okay? You can't assume you're at rest. It doesn't say you're at rest. And we're probably not at rest, actually, to begin with, at least. But I do know my acceleration is 2 meters per second squared. That's the same throughout. All right. Now, what's going on at 4 seconds? Well, 4 seconds is 4 seconds. I don't know what position we're at. I don't know my velocity, but I do know I'm still at 2 meters per second squared for my acceleration. At 5 seconds, I know that I'm 30 meters ahead of where I was before. So notice what I put here. X of 5 equals x4 plus 30. So that I don't know that, but I know a little bit about it. I know I'm 30 meters ahead from where I was a second ago. I don't know the velocity at 5, but I know my acceleration is the same there. And this part right here, this acceleration is not that important, actually, because this acceleration usually describes what's happening afterwards, so we don't really need to know that. All right, that's it, by the way. Now, once I've got all this, I say, okay, what do I need? What am I asked for? I'm asked for the velocity at t equals 0 seconds. So what I boxed over here, what I need to know. And is there anything in the problem that's going to act as a support that helps me figure that out? Well, velocity 4 is something I'm going to need to know to figure out the initial velocity. Now, let me show you something here. We have done the physics. The physics is completed. What I'm going to box here in blue. Oh, come on. Be nice. Be nice, Zoom. Okay, Zoom is not. Okay, that was user error. Sorry, Zoom. I didn't mean to. Sorry, Zoom. All right. Oh my gosh. Why can't I do things? All right. Everything I boxed here. Motion diagram, specifying the variables. That's the physics. And the physics is done. The rest is math. So now I have to, after the physics is done, and I figure out what I know and what I don't know, now I start to look at my equations, which I see. I drew them down here. Okay, these equations. And I look at these equations and say, what things do I know and what don't I know, and how am I going to use these equations to figure out the unknowns? That's what I'll need to figure out. Okay. Let me clear this out. All right, so I need to know velocity 4. I know some information about time, so I definitely want to use a time equation. But I need to get a velocity out of things. I don't want to use equation 1, though, because it involves 2 velocities. And I don't know any velocities. I like equation 2 because it does contain 1 velocity and other things that I actually do know. And I don't like the last equation because it doesn't involve time, and I have a lot of time information. So I'm going to go with equation 2 here. I'm going to move the x4. So I wrote it out in terms of the variables in the problem. So the final position, the initial position, that's x5, x4, v4, delta t, so on. So I move the x4 over to the other side. The difference there is 30. I put all the other numbers in. Do your math. You get 29 meters per second. Then I can now refer back to equation 1, and I can figure out what's going on at t equals 0 seconds. So my final velocity is 29. I don't know my initial velocity. I know my acceleration, and I know the delta t. And I find that my initial velocity was 21 meters per second. So that's an example of how I'm utilizing this method to solve this problem. Do you have to use this method? Certainly not. But I think this is nice because it's very organized. And like I said, there's a lot of consistency in this. When we do other problems, they're going to be done in a very similar fashion. What you should find to be the challenge is creating these variables and their numbers. That should end up being what's hard. Because once you get that, it's just a matter of looking at the equations and trying to figure out what goes where and how to do the math, which is not a physics thing, So let's go to another problem. Let's just get to another problem. Unless there's a question about this. Anybody have a question about this one before I move on? I think I immediately have another problem, though. Yes. A driver has a reaction time of half a second. And the maximum... Uh-oh. The word deceleration's here. My bad. You didn't see that. That's not there. Okay. A driver has a reaction time of 0.5 seconds, and the maximum acceleration of her car is 6 meters per second. Okay, I don't like the word deceleration. My bad. She's driving at 20 meters per second when she suddenly sees an obstacle in the road at 50 meters in front of her. Can she stop the car in time to avoid a collision? All right. There's 2 different types of motion taking place here. We have the half second of constant speed, and then subsequently we have slowing down. So I'm going to draw a motion diagram that shows that. Okay, I'm just going to put 2 points for the constant speed part because it's just so quick. Then afterwards, I show slowing down. The vectors get shorter and shorter, and I'm showing acceleration points to the left. It's a negative acceleration because I've decided that we're talking about moving to the right. So that's what I'm going to do there. Now, I want to put motion at the end, here, at the beginning, and any intermediate step where I know things or something happens, and that's the after the reaction time. Okay, so let's label stuff. At the beginning, t equals 0, x equals 0, initial velocity is 20, no acceleration to begin with. I know everything about the start. What about after a half second? Well, a half second goes by, so it's half second. The distance is 10 meters. The velocity is 20 meters per second. And the acceleration at this point is a -6. Now, when you look at this and say, well, wait a minute, how do you know 10 meters here? Because that's not given to you in the problem. It's true it's not given to you in the problem. However, it's very easy to see that it's 10 meters because you're coasting for a half second, right? So how much ground are you covering in a half second? Well, when you go 20 meters per second, a half second, you're covering 10 meters. So I know that when we finally do hit the brakes here, we've already traveled 10 meters. So I put that in here. You could leave that as an unknown too, but it's just so simple to do. I just put it in there. At the end, this is where maybe it's a little tricky here. How am I going to go about doing this? Well, the way that I have decided to go about doing this is to assume the velocity is 0 at the end. And then I want to work out what position I'll be at. And I'll know if I hit the obstacle or not, because either this position is going to be under 50 or it's going to be over 50. And that's how I'm going to decide to do this problem. It's not the only way to do the problem, by the way. Another way to do the problem is to assume you reach 50 and then check your speed. If you're still moving, well, you hit it, right? So I just happen to go about doing it this way. So I don't know how long it's going to take me to stop. I don't know what position I'm going to be at, but I do know my velocity then will be 0. And the acceleration at that point is irrelevant. So I'm not even going to put it. So what do I need ultimately? I need to know x2. And that's it. I just need to know x2. So what is it going to get me there? Well, I don't really have a lot of time information in this problem. So it sounds like equation 3 is the way to go. Sounds like it's the way to go. So I'm going to do that. Equation 3, the velocity squared equation. So in terms of the variables I've defined, it'll be v2 squared equals v1 squared plus 2a and the difference of the two positions, x2 minus x1. And I know everything but x2. Plug in your numbers. Make sure you have your accelerations negative. It's very important here. Solve this. We get a 43. We get a 43. And that's under 50 clearly. So 7 meters away. That's when she stops. Okay. Any questions about this one? This is a good one too. You see this problem a lot in physics because, so the reason why you see this problem a lot in physics because it's used as a demonstration of, like, usually a follow-up to this problem is, okay, the driver, stopped in time. But now let's change the problem. Now the driver's drunk. Let's say the driver's drunk, right? And because you're drunk, your reflexes are not as good, and maybe your reaction time isn't a half second now. Maybe it's a full second. That's how long it takes you to react. Probably worse than that, to be honest. Well, what if it was a full second? That would mean the initial position was 20 when you started to brake, and that means you're going to end up at 53. And that's not good because you hit the obstacle. So, yep. That's a nice little variation. But that's actually surprising, right? Because an additional half second of reaction time. Because 40 meters per second, right? That's around 45 miles per hour. That's what that is. So if you're going 45 miles per hour and you have an additional 0.5 seconds of reaction time because you're plastered, well, that's not good. And that's why people get in accidents so often, because the reaction times are bad. And you move a lot, right? You move a lot in that time. So, great. How are we doing here? Are we good? Everybody's so quiet. I don't know what that means.
So far.
Okay. The other group was super talkative. My earlier group was like, they couldn't shut up, which is fine. I don't mind that. I'm just worried. Just worried. We'll make sure everybody gets it. When it's quiet, I get concerned. Processing. I love that. Yes. A lot of processing. By the way, just so you know, for me, when I took this class, the entire time I was pretty much lost. I had no idea what I was doing the whole time. And this class was weird for me because it was the first class I took where I just didn't sit. Normally I could just sit in a class and just listen to the professor and be like, okay, I get it. And just do it. And this is the first class I was like, damn, I gotta study now. Lame, but it's not lame. It's great. So yeah, you kind of have to. This takes a lot of practice. Nobody can coast through physics. I mean, some people can, I guess, but it does take a lot of study. And you know, one thing that's really challenging about this stuff is this: you got two things working against you. Your intuition about how things work, which is wrong from a physics standpoint. A lot of people's intuition about how things work is very wrong. And the second thing is this class is very much like a math class, but it's not a math class. And a lot of students like to turn it into a math class, which you don't want to do. It's very tempting because if you're good at math, it's very comforting. You want to turn everything into a problem. Like those graphs back there we had. Well, a lot of students like to just take those graphs and just turn everything into an equation and do stuff. You can, but it's not wise. Because you're spending way more time and you're missing the concepts when you do that. So anyway, end rant. Let's keep going. My next problem here is a calculus problem. And I have to show you at least one of these. But again, like I said, I know not everybody is probably comfortable with their derivatives yet, either because you've just started it or haven't maybe, but I'll walk you through this. So sometimes we have problems where we are actually told what the position function is, and then through calculus we can work out all the other things. And the relationship is this: when you have your function for position, you can take its derivative and get a velocity. You take the derivative of that, you get an acceleration. Because this is a polynomial, we use the power rule for derivatives, where when you take the derivative of a polynomial, you use term by term, you move the exponent of the variable to the front, and you subtract one off. So for example, if you had x cubed as your function, and you want to take the derivative of it, right? You move the 3 to the front, subtract 1 off the exponent, you get 3x squared. So that's what you're doing for all these. So if I'm asked for what the position is at 2 seconds, well, I just need to plug in 2 into the equation, which I've done right here, and we get a 7. For the velocity, I'll need to take the derivative of the equation, which the first term, 2t squared, becomes 4t. I move the 2 to the front and multiply it by the coefficient that's there. The t becomes t to the first power. Minus t just becomes minus 1, because the variable has an exponent of 1. Now it's 0. And the derivative of any constant is 0, because there's no change in it, right? So that's my velocity equation, and if I do that again, I get my acceleration equation, which is not really an equation, it's just a number. It doesn't matter what time it is, the acceleration is always 4. If I plug in 2 seconds to my velocity equation, I get 7 meters per second, and then the acceleration, of course, is 4 meters per second squared. So those are the parameters, those are the position, velocity, acceleration at 2 seconds. They ask some additional questions here. Does the particle have a turning point? That would occur whenever velocity is 0, right? Because then you're changing direction. So for my 4t minus 1, I'm going to set that equal to 0 and solve for t, which we get a quarter. There we go. That's it, I think. Yeah, that's it. That's the problem. So I don't like to do this too much because this is just a math problem. There's no physics involved here. So it's not very interesting, but I still got to at least show you one of them. Okay. All right, so how are we doing on time? We're good on time. We have one more topic to cover before we wrap this up and get into the lab. So we've been dealing with one-dimensional motion so far, and that's fine. The one-dimensional motion, we've been talking about X quite a bit, but it could be any one-dimensional motion. It could be Y, or it could be something in between, like an incline or something like that. If our objects are falling under the influence of gravity, so our one-dimensional motion is vertical, and there's nothing else influencing the object, then the object is said to be in free fall. And it has a constant acceleration of 9.8 meters per second squared, vertically downward. Now notice this vector that I mentioned here, vertically downward. I've given you this vector in magnitude direction format. Notice that I did not tell you it's negative 9.8 meters per second squared. Okay, it could be negative, but that depends if we call down negative, which we do usually. That's pretty standard, but I will say there are circumstances where we might not do that. I would say it's generally safe to assume down is negative, but do look out in problems in case that has been changed for some reason. Okay. For example, here, you don't have to answer this question. I'll just talk about it because we actually had this question already, you know, like, I don't know, what was it, like last class or the class before, I forgot which one, but a ball is tossed straight up into the air. At its very highest point, the ball's instantaneous acceleration is what? Well, it's not zero, right? The speed is zero, but it is negative, assuming we call negative down. But the acceleration never changes. In fact, when the ball is tossed straight up into the air, it undergoes one continuous motion as it goes up, reaches the peak, and comes down. All right. In fact, that is the next problem that we want to do. So let's do that. We have a student standing on the ground, throws a ball straight up. The ball leaves the student's hand with a speed of 15 meters per second when the hand is 2 meters above the ground. We want to know how long the ball is in the air before it hits the ground. So I have a motion diagram here showing the ball going up, coming to a stop, coming back down. That is one continuous motion. Yes, we changed direction at some point, but the acceleration never changed. So our set of kinematic equations can describe the entire motion. You do not have to break it up into going up and coming down. The only time you ever have to break up a problem is if the motion ever changes in the process, which means the acceleration changes at some point. That's not happening here. Also, another really important point here, super important point. Technically speaking, when we analyze this problem, we are analyzing it from the moment the ball leaves the hand. We are not concerned with how the ball left the hand. All we know is that it left the hand at 15 meters per second. The actual process of throwing is not of interest to us here, and I will not put that anywhere in my problem. Same thing, it goes up, it comes down, and it's going to strike the ground. But we want the moment just before it hits the ground. We don't want to talk about it hitting the ground because there's a whole different acceleration happening there. There's a collision. There's a whole bunch of physics there we're not ready for. So we're not considering when we hit the ground. So you don't want to say, for example, the velocity is 0 when we hit the ground. No, you want to say what the velocity is the moment before it touches the ground, because that's all the influence of gravity. Okay.
Professor?
Yeah.
Wouldn't the ball slow down as it reaches?
Well, we are going to assume no air resistance for the vast majority of our problems. Unless I tell you otherwise, there's no air resistance in our problems. That is a very difficult problem. So if we throw an air resistance, see, this is all just algebra right now, right? If you throw an air resistance, you have to solve it with a differential equation. Like, that's how much more complicated it gets when you put an air resistance. And we're going to do a little air resistance, but we're going to be very limited in what we can do because we don't have those tools of differential equations. So you're right, but it's a simplification we're going to make. And again, unless you're told otherwise, there is no air resistance. So,
Got it.
Okay. So to start, t equals 0, 2 meters off the ground, y is 2. Initial velocity is 15 meters per second. The acceleration is negative 9.8 meters per second squared. That's the start. Then I have to create something at the end. Again, I don't care about the top. You could work it out if you want to. It's not important. It's not relevant. It's just adding time, but you can do it. I don't know how long it takes. I do know I'll basically on the ground is going to put a y equals 0 here. I don't know my speed, and my acceleration at this point is irrelevant because I'm about to hit the ground. So I wrote the equations here, just substituting Instead of A, I put in a negative G. I am calling down negative, right?
Professor, someone asked in chat how you found A.
How I found A? Well, that's the whole point of this, right? If we're talking about vertical motion, the acceleration is 9.8 meters per second. Every time you're dealing with free fall motion, you got to know that's always the acceleration. So it's not given to you, and it won't be given to you. You just got to know. Vertical motion, without the influence of any other factors, the acceleration is negative 9.8. If you say negative is down, by the way. So that's why. Okay. All right. Now, so which equation should, well, what do I want here? I want time, right? I don't have final velocity. So I can't really use equation 1 or 3 because I just don't know the velocity. I mean, I guess I could use equation 3. Yeah, you could use equation 3, but it doesn't give me what I need. You'd have to use equation 3 and then come out with another equation. So I'm going to go with equation 2 here because I do know everything except for time. The only downside to this, it is a quadratic, which is not the worst thing in the world. It's just a little, it's a little tedious to solve a quadratic. But anyway, you solve the quadratic, you get 2 times. One's negative, that's nonsense. Or the other one is 3.2 seconds. So it looks like it took 3.2 seconds for the ball to go up and come back down. All right. Fantastic. So it's a one-dimensional problem, just like the stuff we did before, with one added little thing. And that's the acceleration due to gravity. Okay. Got one last thing to cover here. Thank you for being troopers. I know it's a lot today, but we're almost done with this. I got one last thing to tell you about. One last thing. So you will use 9.8 meters per second when the object is in free fall. It's freely fallen without any other influences. If an object is falling like down an incline or something, you could still solve those problems pretty easily. So say we have an object that's sliding down an incline. The reason why it's sliding down the incline is due to gravity, but it's not experiencing the full extent of gravity, right? Because of the incline. In fact, if you see this picture down here, we have an acceleration that is downward, but I'm going to break that into components that follow the coordinate axes. The acceleration, Daniel, the acceleration is 9.8 meters per second squared. Negative if you choose that direction to be negative. Okay, like here's a good example here. Well, let me get through this and I'll kind of explain something here. Now I'm going to break this up into components. There's a component along the incline and a component perpendicular. The component along the incline is what's responsible for the motion. The perpendicular component will not move the object. So that means we can see here that we have a fraction of gravity here. Now when I make this triangle, that triangle is similar to the larger triangle that is the ramp, and it turns out that the ramp angle and this angle here are the same. So to find out the parallel component of acceleration, I will need to use my sine function, right? Sine is going to be opposite over hypotenuse. So that's the equation you see right here. The acceleration along the incline will be plus or minus g sine theta. And that's what the alteration is. When you're going down an incline, you're experiencing a fraction of gravity. And that fraction is determined by your sine of the ramp angle. Now, I worked this out here for you as an example, but you never need to work this out again. Just always know that if there's inclined motion, your acceleration is g sine theta. Now, I did put a plus or minus here because it depends on what you call positive or negative. Now, here's a good situation where it's not clear what you would do. We want a tilted coordinate system here for sure. Right? We want a tilted coordinate system here. That's along the ramp. But we're going right and down. Right is generally positive, down is generally negative. So, you know, which way you want to go with this? Like, it's up to you. Just be clear about what direction you're calling positive and negative. I like to call the direction down the incline to be positive in this situation. Up the incline is negative and down is positive. That's just what I like to do. You can do it any way you want to, though, but just make sure you're consistent throughout the problem. Okay, last problem, and then we're done. Last problem, and then we're done. We have a skier gliding along a 3 meter per second horizontal frictionless snow. He suddenly starts down a 10-degree incline. His speed at the bottom is 15 meters per second. We need the length of the incline and how long it takes from the reach to the bottom. So I've drawn a picture of that. I have my horizontal frictionless snow. I got my 10-degree incline, and then I got the bottom. And I drew a little motion diagram showing my speeding up down the incline, right? And I'm going to take the starting position to be at the top of the incline and the final position to be at the bottom. So t equals 0 at the start, s equals 0 at the start. I'm using s because, you know, it's not really x, not really y. It's kind of a generic direction. S is just along the path here. So s is 0 here too. The speed is 3 meters per second, and the acceleration is going to be positive g sine 10 degrees. Positive because I'm calling down the incline positive, and g sine theta, that's the acceleration for an incline. So really, all you're doing here for your acceleration is just, you got to know what the ramp angle is. That's it. And then your acceleration is just 9.8 times whatever the sine of the ramp angle is. At the end, I don't know how long it took. I don't know how far we went, but I do know I was 15 meters per second at the bottom. And I don't care about the acceleration there. Equation 3, which is the velocity squared equation. I know both velocities, so that's a good idea to use that one. And I get that my delta s, the distance down, is 63 meters. That's along the ramp. If I want to find the height of the ramp, which I'm not asked for, but you just do a little, you know, triangle here. H is delta s sine 10 degrees. But we're not asked that, so I'm just, but there's a lot of problems where you are asked, you know, what the height is. I can use equation 1 to figure out the time. I know the velocities. I just solve for time. I get 7.1 seconds.